In this unit, we're going to discuss some general principles of main group chemistry. That's the chemistry of the main group elements in the S block, groups 1 and 2, and the P block, groups 13 through 17, really, since the noble gases don't do much. And actually, we'll look at some specific classes of compounds here involving hydrogen and oxygen, but actually the general principles we'll develop at the start of this unit are the most important thing in the entire chapter. These general principles of Lewis acid-base reactivity, reactions where pairs of electrons move around, apply to inorganic chemistry, organic chemistry, and the vast majority of chemical reactions in general. And so they're extremely important to understand, rationalize, and predict chemical reactivity. And if you're a chemistry or biochemistry major, or you go into a career involving chemistry or biochemistry in any way, shape, or form, you're going to apply these principles in your future career. So they're really important to start getting a feel for now so that you can apply them for success in your organic chemistry courses for the most immediate term issue. So we're going to start with these general principles of chemical reactions, chemical reactivity, particularly ionic reactions where ionic intermediates are involved and pairs of electrons move around, meaning there are changes in charge that are going on. Then we're going to look at some specific classes of compounds where we can apply these principles, starting with compounds of hydrogen, and then looking a little bit at compounds of carbon, inorganic compounds of carbon that don't really involve carbon in small molecule form, and then compounds of oxygen, oxides specifically. And so once we finish this unit, we're really going to get some important general principles for the reactivity and properties of the main group elements and compounds thereof. And so Lewis acid-base theory is going to be really important for that. We're going to generalize out the Bronsted theory and develop extremely general principles of chemical reactivity. We're going to introduce some new terminology around this, electrophiles and nucleophiles, which give us a sense of Lewis acidity and Lewis basicity. And then we'll look at compounds of hydrogen and study the different types of hydrogen-containing compounds. We've seen a number of hydrogen-containing compounds so far. Most of those have been covalent hydrides. We'll introduce ionic and metallic hydrides in this unit, and we'll discuss the barriers to an economy based on hydrogen. Hydrogen does display some reactions that we can use, for example, for energy production, but there are some barriers there, and we'll discuss those. And then we'll talk about the allotropes of carbon, forms of carbon in an elemental and sort of inorganic form where it's not bonded to hydrogen or oxygen or other sort of more traditionally organic elements. And then we'll dig into the chemistry of oxygen-containing compounds in the form of the oxides and learn that there are different types of oxides. And in fact, we've seen some of these different types already. There are oxygen-containing compounds that are acidic, there are those that are basic, and there are those that are somewhere in between that we call amphoteric. And we will learn how to classify reactions of the hydrides and oxides and think about them rationally based on what's present along with the hydride and oxide and how we would expect the hydride or oxide to react based on its inherent structural properties. Building a bridge from structure to reactivity, that's actually really important, right? Being able to look at a structure and make a rational prediction of its reactivity is a big part of this unit as well. Let's begin with general principles of chemical reactions. Obviously, a hugely broad idea. What are the general principles that govern chemical reactions? Let's go back to basics to start this discussion off and talk about what a chemical reaction actually entails. What does chemical change actually involve? And really, there are two general ideas here that we want to keep in mind. The first is that chemical change always involves the rearrangement of atoms and or electrons. And the movement of electrons in particular is really important here. Electrons moving to form or break bonds is essential to chemical change. But along with chemical change always comes a transfer of energy as well. And we've talked a lot about exothermic and endothermic processes, for example, in Chemistry 1. And the transfer of energy always comes along with chemical reactions as well. Two very general principles to keep in mind. What actually happens during a chemical reaction? Well, for reactions that involve the movement of electron pairs, which are the most common type of chemical reaction, there's a general principle that we might call the Lewis acid-base principle that helps us describe and rationalize and even predict what's going on. And so I'm going to work with an example on this slide to describe the general principle, and there are really 3 different ways we're going to talk about this principle using different language that all really goes back to the same essential idea, and we'll make that connection at the end of this slide. So for the example here, if we mix ammonia, NH3, with borane, BH3, a chemical reaction is observed, and specifically what's observed is the formation of a bond between nitrogen and boron derived from the lone pair on nitrogen. So in the product complex, this is a Lewis acid-base complex, we formed a bond using those electrons from the nitrogen atom. And what's happening here is we start with an atom that has relatively high electron density, right? A non-bonding lone pair, relatively high energy electrons. And those electrons are heading to an atom that lacks an octet of electrons in the boron. It's electron deficient. This pattern of bond formation from atoms with high electron density to atoms with low electron density is key to the Lewis acid-base principle. Electrons spontaneously go from atoms or molecules in which they are in high density to atoms or molecules in which they are low density. There's a currency metaphor we can use here, where money tends to flow from those with a lot of it to those with less of it. Perhaps not in practice, but at least to make the analogy, this makes sense, right? Electron density goes from high density locations to low density locations. Now, that's a bit of a mouthful to describe, and so we use some shorthand terms to describe those molecules or atoms with high electron density. We call those nucleophiles, since they're nucleus-loving, and we call those atoms or molecules with low electron density electrophiles, and we can say in general that electrons spontaneously go from nucleophiles to electrophiles. A third way to talk about this principle uses the idea that the electrons that are actually donated are in a molecular orbital that is relatively high in energy, the so-called highest occupied molecular orbital in the nucleophile. And where they are going is an unoccupied or empty orbital in the electrophile that is the lowest energy unoccupied orbital, or LUMO. So in general, this is probably the most abstract statement of the principle, but we'll see this idea applied to this specific example in a couple of slides. Electrons spontaneously go from the highest occupied molecular orbital to the lowest unoccupied molecular orbital. So again, the general idea here is that electrons go from molecules or atoms where their density is high, right? There's a lot of electron-electron repulsion there, for example. So the electrons are a little bit uncomfortable, for example, in the highest energy occupied molecular orbital. Those electrons go to a place where the electron density is relatively low. Maybe there's positive charge, partial or full. Maybe there's a very low energy orbital that's empty that those electrons in the nucleophile would like to go into. That's the LUMO, right? From the high electron density regions to the low electron density regions. Extremely important general principle here. These interactions between the electronic haves and have-nots, if you will, are at the heart of most organic and inorganic reactions. So the slide mentions inorganic reactions, but most organic reactions involve the same basic principle. Nucleophiles react with electrophiles, Lewis acids react with Lewis bases. And let's define the terms Lewis acid and Lewis base on this slide, just so we're 100% clear on what we mean by these. So a Lewis acid is an electron deficient or electron poor species, atom, molecule, etc., that accepts electrons in Lewis reactions. This is the molecule or atom where the electrons are going. And where those electrons are going in a molecular orbital sense is an empty or unfilled orbital in the Lewis acid that is low in energy, what we call the LUMO. Where the electrons are coming from, well, that's the Lewis base. And Lewis bases are electron-rich species. They have high electron density, and thus they donate that electron density in Lewis reactions. And the electrons that are donated come from the highest energy filled molecular orbital in that molecule, or what we call the HOMO. So a general picture of Lewis acid and base reactivity is something like this. At the bottom of the slide, we have a base with a pair of electrons that is donated to the acid to make a bond. And in a formal charge sense, this leaves the base formally more positive than it was in the reactant, and the acid more negative than it was in the reactant. And so there has been a transfer of charge, or a transfer of electron density from the base to the acid. The general idea that Lewis bases donate electrons to Lewis acids is at the heart of Lewis acid-base theory and Lewis acid-base or Lewis-type reactions.